desktop like this, and I'm hoping that I can find my, okay, you should see ontology from graph signal processing.
Yes.
Okay, great. I'm going to go pretty quickly. So John and I and the team, we're about, maybe close to 20 people, actually. We're still working in stealth mode. So what you're going to learn here is probably world premiere of the combined, 40 years of our background. We've built a brand new neurosymbolical logic virtual machine. There are some very, very well-known libraries, which are about 3 to 5 years old. You can look them up. One is called the Combinatorial Basic Linear Algebra Subroutines Library. It's called COMBLAS, on which there's built GraphBLAS. And it also supports a whole range of matrix operators. So instead of doing discrete symbolic computations, you substitute the discrete symbolic world for matrix operators that produce the exact same thing as if you had done a symbolic computation. And I won't get into this too heavily, but I will show you a couple of things. One is this has an extensible instruction set architecture. Most virtual machines have what's called an ISA, which is the instruction set architecture, which is the primitives. There are 22 primitives in here, but they are arranged in the format of a row of instructions and a column of instructions as indices. And this matrix, as it runs in the virtual machine, is self-observed, and the transition probabilities are recorded. So its subgraph of activation is actually learned. And if it's common enough, then the system can perform ontological supercompilation to create a new instruction set, adding it back in. So it's a sort of a self-extending virtual machine. We chose a Prolog super subset, so it handles higher order logical terms, meaning functors can be very complex variables. They can even be fully meta-variabilized, meaning that the variables themselves contain patterns of variables. Again, I won't get into that because we don't have the time, but it is a system for differentiable neural and symbolic integration. So a little bit of what we're doing, one application is in ontology synthesis. And so basically you feed some documents in. I'll talk a little bit about the seed ontology. You can have no seed ontology, but when you have a human in the loop, it works really well because now you can seed the exact concept. So when John was showing his conceptual graphs and you had things like agent, patient, theme, and so on, you can actually add those concepts into this and it will automatically bootstrap. The basic format is you take a document and you convert it into a text and term matrix. And then you can do some operations to this. You can create Laplacian operators, which is a form of a distance matrix, and you can then do other matrix computations. Ultimately, you end up with spectrograms or spectral matrices. These structures are in the emerging research today. It's called graph signal processing. If you take many documents and you have, let's say, 50 matrices, a really trivial way is you take the 50 documents and the 50 matrices and you just add up all 50 matrices and divide by 50, right? So you get an average. Now that's not a very smart way to do it. There are actually many, many more interesting ways to combine these matrices so that you have a perfectly square matrix, and it's generally square and sparse. So that's something to know, and one can reuse current mainstream architectures like the matrix market format or the leucine vector format to actually represent these things. So there is a lot of common infrastructure where you don't have to rebuild everything from scratch. However, the techniques are quite new. When you have a human in the loop, you get this matrix, and I'll show you what one of them look like. But what you can do is you can extend the number of rows and columns. So if I have in here something like a Saab, a Mercedes-Benz, a Toyota, a Volkswagen, I can add a term into the column that says, this entity is of type vehicle or car or four-wheeled vehicle, right? And so now what will happen is the system will enrich its linkages very, very quickly, and you can get some very powerful results out of it. Of course, instead of having a human, you can just take a resource. And you can take combinations of these resources and they can be converted into matrices as well. And I'll show you a little bit of what kinds of results we get. Here's a very simple graph, right? So very simple. Everybody knows the penguins can't fly, and birds can fly, and they have feathers and so on. So I won't belabor this, except there are some measurable weights of a bat is sort of like a bird, but not really. But a bat does have flight, and by the way, the numbers can vary entirely qualitatively. Why? Because we have a way to normalize all these things. So it doesn't matter. So you can get, what's important about these numbers is you can allow subject matter experts who have their own internal system of metrics to give you any kind of graph inputs you want, and you don't have to tell them how to do anything. You just use their natural way of ranking. What happens is, bat is to bat, well, that's going to be the whole diagonal is going to be 1. I could have made them all zeros, but bat is isomorphic to bat, so we just call it 1, and you can calculate distances. So bat to bird, which is 1.7, and here you can see in the graph it's 1.7. So that's how that matrix was done. It's lexicographically ordered, meaning you just sort the words in alphabetical order. You then, when you set up the matrix of these distances, you want to be able to normalize them. And so what we do is we take the determinant of the matrix and we divide all the values by the determinant. And that's how we get the normed matrix. The fancy stuff comes when you do the eigen decomposition. And here inside this decomposition, we're calculating something called the matrix exponential. And you have to do a little bit of tricky handling here and there because you don't want to have redundant paths, meaning paths that are counted more than once. But once you do that, you can then ask questions. And this is what the resulting matrix looks like. It's an operator, meaning it's not the thing itself, but it's the thing that gives you the answer when applied to other things. And so if I ask, what is most like a bird, but least like flight, right? I'll get bird in the first position and ostrich in the last position. And oddly enough, it puts penguin third from the last. So I guess it can sort of run for whatever reason, the graph has it like this. So you see some oddities. What's interesting about this is I can ask about bird. Of course, the first rank will be bird. Birds have wings, then flight, and of course, ostrich is last. But if I go from penguin, right, you get bat as being sort of least ranked to penguin, rather than an ostrich is closest ranked to penguin. So you see that is in the second place, and of course, ostriches run. Now, if you take these graphs together, you can actually stitch them together to create a proto-ontology. And when you read the diagonals of these vectors, as you do the multiplications, what the Fiedler vector means is you resort the matrix. In other words, its lexicographic ordering is sorted from largest value to smallest value down the diagonal. That's what the Fiedler vector is. And I thought what I would do is show you very, very quickly a real world application of this. I actually gave a talk last year to the United States Technology Leadership Council on the subject of, this comes down to what's called quantum graph signal processing and graph signal processing. And if you look at, like, for example, Hitler's speech from 1939, and let's take a 30-year jump. So I'm just giving you an example here. Here's Hitler's speech. Here's Dr. King's speech 30 years later. And then 30 years after that, here's bin Laden's speech. What was really interesting is our customer wanted to understand how to group personalities together so that you could treat one personality in terms of another and thereby predict what such a personality might or might not do. And I'll leave it to your imagination to figure out what kinds of customers we have. Here is the answer. If you look at bin Laden before the attack on the US embassy, you get this spectrogram. But notice that this spectrogram with its peaks and troughs is really similar to Hitler before his attack on Poland. So this is going across 30 years. And if you now do what's called just digital signal processing, like autocorrelation between signals, you will get that Hitler is most like bin Laden, and that the both of them are least like Martin Luther King. And so I thought you would find that interesting. You know, we created a workflow where everything I just showed you allows us to do some very powerful machine learning by learning these patterns and then using them to analyze arbitrary inputs, categorize, and treat them in terms of those proto-ontological concepts. So who would be a modern analog for bin Laden today, or an Adolf Hitler? So those are the types of questions. And a lot of the work that's going underneath this involves mostly the combinatorial BLAST library and our extensions for operator theory and the graph BLAST library. They were developed by the United States Department of Energy. They've developed over the last 5 years, and they're the most advanced scalable libraries available in the world. You can run it on one computer, or you can run it on an entire cloud of GPUs as big as you want to scale. And, you know, essentially, you know, our goal, our product is called Semantic Radar, product of GraphStacks, and it involves the, you know, the neurological virtual machine built on this graph basis, which combines all the lessons learned that John just shared with you in graph signals processing, but with symbolics injected into it, which traditional deep learners do not have. And that is my quick, fast intro and talk. Thank you.